this is the recording for the Centripetal Force lab and experiment, and here we have the motivation. Lots of machinery use rotating parts, and they have to pay attention to the centripetal force. There's actually no such thing as centrifugal force. That's actually simply the inertia that wants to keep things outward. But in order for things to rotate, they need a force towards the inside. Otherwise, they wouldn't be able to rotate. They would just fly off. So it is a centripetal force. All right, let's get going here. Objectives, theory. The theory it always gets me looking at the theory because it's a total geometrical proof how we come up with that equation that says that the centripetal force equals mass times velocity squared divided by radius. Anyway, here's the theory, relatively short actually. This is kind of what the experiment is going to look like. So we have a little pipe here through which a string is threaded, and then we have an object here, and this will rotate, and here in the third dimension, kind of like out of the screen into the screen and so on. And then the other hand here will hold on to the string with a spring scale and measure the force. All right, let's see. This would be the equipment here. Actually, this would be here the mast, these rubber stoppers all tied together. Here's that pipe I was talking about. The string is kind of invisible lying on the table here. Oh, there it is. And then here's a stopwatch. There's a scale in order to measure how much mass is on there. And then there's a spring scale to actually measure the force. And you will see that when I actually do the experiment. So here's the oh, I guess I could have used this one here instead of showing you that one earlier. So here, by the way, this piece of tape here needs to be there to make sure that this length up here is constant, so it doesn't slip up and down through here. So that's why that piece of tape is there. All right, we will also see that when I'm going to measure the force here, that this little pointer right here is going up and down vigorously because I just cannot do it exactly consistently all the time. And then I think I'm going to take an average there. All right, here we have the data and analysis, and these two big nice equations. The second one here is the centripetal force equation. This one here is relating the speed with which it rotates to the circumference. That's why you see 2 pi L. L stands for the radius in this case, length of the string up there. So 2 pi R would be the circumference divided by the time it takes to go around. And I'm going to measure how many rotations there are. So these two big equations here, and that is actually going to be in Excel. So turns out if you want to check those equations, please do so. But other than that, Excel is going to do all that computational work for you. All right, I've got two tables here. One of them is just my example, and this here is the actual data table. Notice in my example, I'm going to have these errors here, so I'm comparing the force with which I have to hold on, 3.8 Newton. Apparently, I measured every time on average in my example, to the centripetal force that was actually calculated, and I was doing pretty good for those. I will do a couple more examples that you then will see in the Excel sheet as well. All right, so then table 2, that will be the data that I'm going to take, but you have to evaluate them from the video that I show you. And then we're going to do the whole thing again with the applet, and that would be this one here. I'm going to click on begin just now, and I will explain that a little later when we get to it. What's going on here, you can see that's pretty much the setup. This is how it would look like, and then we're going to do the applet, and we're going to do these tables then again. These here. All right, that's actually it. No conclusion. The addendum, we don't need that error propagation here. I will just have Excel do it for you. And then there's an addendum 2. Due to liability issues, the following is highly discouraged. I have to admit, I actually have never tried this, what I wrote here. That would be kind of cool. And what I envision is drive with a car on a parking lot in a large circle around and put some cones up there so I know that it's a circle, and then somehow measure the centripetal acceleration. I'm envisioning a pendulum, which is, by the way, I think where you saw pendulum early in the theory part. So hang a pendulum from the ceiling in the car, and then as you turn and turn and turn and turn and turn, that pendulum actually will swing from the pure vertical due to the centripetal acceleration, respectively, its inertia. It wants to stay outside. And that's where you see your turning car pendulum. Or actually use a cup with water and observe how, when you're curving, when you're turning, how that water actually begins to slope towards the outside. Again, that would be the inertia of the water. But again, I'm not going to do that. Never done it either. Due to liability issues, I actually highly discourage that. But it would be a cool experiment. All right, and let's get going. I'm going to show the actual experiment first, which I still have to tape. While here in the video, you will see as if there was no time lag, I guess. All right, let's get going. Right, this is an introduction to the experiment for the centripetal force experiment. I actually already did it, and you will see that I'm hitting myself in the head at least once. So what I have here is actually 6 times that experiment. So here's one, for example, and I'm swirling it. You will see that that turns around. By the way, I'm swirling it horizontally, so that gravity at every time is pulling down like that. If I swirled it vertically, then gravity would pull towards the middle, and then at the bottom it would pull away from it, and that would just upset the results. I'm actually quite satisfied with the results that I got. Interestingly enough, the very first one I had, this one over here, which has the heaviest rubber stoppers on them, actually gave me the worst error, kind of like around 30%, while the others were actually pretty good, what I did. These rubber stoppers here, they all kind of look equal. Of course, they kind of make it safe so that if I let go or something, or if the string breaks, it's hopefully not going to do too much damage. Interestingly enough, there are actually 2 kinds of rubber stoppers with these holes, because some of them are, like here I have 3 and 3, and they're actually not the same. They're quite different in their mass, I think. Or this one here is just really close to that one, something like that. Anyway, before I actually swirl these here, I have to make certain measurements. So for example, this one here, we can see this is the length here. So I have to measure the length with a meter stick or ruler, and I have to pay attention that this little tape here has to be right beneath it, because that's when I'm swirling it. I have to make sure that this one is right beneath it to keep it constant at a constant radius. Over time, I guess students added more and more of these little tape thingies here, and so, oh well, that doesn't matter too much. The other thing that I'm going to measure before the experiment is how much mass I have on here in these rubber stoppers, so that's what I have to scale here. And then I have a timer here, but that's really was only for my own purposes, that I kind of figured, okay, I'm gonna tape myself for about a minute, and then you actually, as you're watching the video, you have to figure out which 30-second part are you gonna take in order to count the number of rotations. So I give you enough time there to start it at some point and then stop it 30 seconds later, counting the number of rotations. Some of them are really fast, so when I analyzed my own data, I had to count really fast at some point. In fact, at the very last one, the one over here, that is actually its small mass on a short string. I had to rotate it really fast. At some point I ran out of counting, and you know, I'm counting in German, so here I am, 1, 2, 3, 4, no, that's what I did. I did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. You know, I had to stop after like 18 seconds, so that's up to you on the very last one if you actually want to stop a little bit earlier. So you would have to measure that. Other things, oh yeah, you will see that it actually droops with the angle here. You will have to estimate what kind of angle that is. Turns out, actually, if you estimate 10 or 20 or 15 degrees or 25 degrees, something like that, it really doesn't matter, because the angle goes into both formulas for the amount of force with which I'm pulling and the centripetal force equally. So it really doesn't matter. I will show you that in the analysis, if I don't forget to do that. Let's see what else to point out. Yeah, so as I'm turning this on here, I'm holding the spring scale like that. I have it tiered upside down. And then this
pointer here is just going up and down vigorously, and I was trying to go for an average, and that's what I try to keep in mind in order to measure that. Also, if I turn it faster, of course, I will measure more, but if I turn it faster, that also means that I measure more tension in the string, and that I measure more centripetal force, or compute more centripetal force. So if I turn it fast and measure more here, it's just the same as if I was turning it slowly and measure less. The error should be approximately the same there, respectively. The two results should be approximately the same. Let's see if there's something else I wanted to point out. I already said about bonking myself in the head on this one here. I think there's just one other thing. Oh, I was wearing my reading glasses all the time so that I could look at this one here. Oh well, that's actually it. All right, so that's the introduction, and the next 6 minutes or so will be the actual experiment with these 6 different setups.
Right, here in this recording, I want to show you the analysis of some of the data. I'm looking here at the lab manual, of course, and these are examples from a long time ago. So I just put them on the Excel sheet. You will see them in a moment. If you had noticed earlier, actually, these numbers were off earlier. So I fixed them looking at Excel. Anyway, here they are. Here are the same data in Excel. And now I'm going to look at, okay, that's not supposed to read example right there. The example is going to be on the next line. So with today's data, so I'm going to put these in right here. So I measured 4.5 newtons with the spring scale. That's kind of what I was aiming for as I was doing that. And then before I started it, I measured 123 grams for the rubber stoppers and a length of 51 centimeters above the little pipe thingy there. And then I watched my own video, and in 30 seconds I counted 35 rotations. And then I measured an angle, or estimated an angle of 20 degrees. It was the one that was actually drooping the most. And so I have a tension force here of 4.2 newtons pulling on it, while here I have a centripetal force of 3.2 newtons. That it should be, so these two results should be the same, 4.2, 3.2. So obviously they're not, so I have an error of about 33%. This, by the way, is the largest one I got here. When you do the calculations with my data, you should come up with pretty good results. I mean, I analyzed my own data and I came up with about 10%. One of them a little bit higher, 3 of them actually lower than those. So that's what you will see when you analyze my data. By the way, I said that the angle, how you estimate the angle, is not going to make a difference. So if instead I was to estimate 50 degrees instead of 20, watch what happens to the error in the back. Right there. It didn't change at all. Yes, if I estimate a different angle, this result is totally different, and this result is totally different. But the error between the two is still the same. So it actually doesn't matter. I'm going to change it back to 20. It actually doesn't matter how accurate the angle is being estimated. Or for example, if I change this one here to 35 degrees, you see the 2% error there in the back? There, stayed 2%. So again, doesn't really matter. So here, fill in the other results here from my videos, and down here, this will then be the applet, of which I'm also going to show you a couple of examples. And maybe this error is quite large here in the back because I miscounted when I watched my own video, but maybe it is that much. I was actually hoping that this one here with the largest mass is going to be my most accurate result, but it's not. The other 5 will be better. You will see that. So this is the applet that I'd like you to analyze. Circular force lab, respectively centripetal force. And you can see the setup here is basically the same thing that I just did in the real thing. So this person here who looks like Isaac Newton maybe is swirling this around. So it says here, this lab will let you determine the speed needed to keep an object in circular motion. You will be able to change the force holding the object in a circle by clicking on the washers. So click on the washers and you get the several washers that will determine the tension that is on there. You can adjust the radius of the circle by clicking on the masking tape that's just below the tube. So they have masking tape just like I did right beneath the tube. Okay, I take that back. I had blue or gray tape. They use orange tube. You can also change the mass of the moving object using these two arrows. So I'm going to show you that. Find the velocity of the object by timing at least 10 revolutions. I actually will go with my time of 30 seconds and then count how many revolutions I have to keep in what I did with the real experiment. So I'm going to click the begin button and here we go. I actually don't need the start button down here, so it's going to be off screen because I do want to put the ruler on in here. And here's what they said. Change the tension by changing the number of washers that are in here. So for example, this is roughly 220 grams, which would be about 2.2 newtons. By the way, if I go above 25 washers, 250 newtons. So in this case, I have 290 grams. Then I actually would have 2.8 newtons because I don't multiply with 10, I multiply with 9.8, and of course grams to kilograms. So, and then it goes on, and then I don't really see if these are random numbers here or if there's a pattern to them. I haven't figured that out. Here, the moving mass I can change. So here we go up to that, and then I guess it goes back like this. Anyway, and then here I can change the length and all the way through here by clicking on that. There we go. And I like this one here because it doesn't give us the most accurate measurement, but for example, this here might be 112 centimeters. Also, when we count the rotations, you know, we might be off by half a rotation or something. So it's not going to give us perfect data, but we have to measure certain things ourselves. And we will come up with some kind of error comparing the centripetal force with which it should rotate here compared to the tension with which which is pulling on. By the way, let me just show you here. This is what would happen. There we go. I like this part here where it actually goes left and right, you know, and then of course we have a middle point, which is also why the ruler, I'm going to pause this one here, which is why the ruler here is in the middle of the zero and not on the edge. And then the other thing I like is that when it's further away, the ball is actually smaller, and when it's closer to us, it's actually bigger. The one thing that is somewhat off is, you saw that in my experiment, the string up here is definitely drooping 10-20 degrees, and here they keep it horizontally, and that's just not possible to do because gravity, no matter where it is, will always pull it down. So you have to have upward tension to keep it up against gravity. So that one is off, but oh well, I think this is a really great applet actually, and definitely serves my purposes. Okay, let's take a measurement here. I'm gonna pause this. Reset, there we go. Let's see, I want to use, let's say for example, a large mass on here, some kind of washer sear, and of course just like the other experiment, let me see, I'm going to change this one here to, yeah, the kind of length there. So just like the other experiment, it depends on how fast you're rotating, it depends on how much mass you have, it depends on the length, it depends on what the tension is, so lots of variables we can change. So here we go. Apparently I'm going to use 250 grams, and for the rotating mass, this one here, the length looks like 114 centimeters. I'm actually jotting that down on the side here. And then I have 19 washers, which is gonna give me 1.9 newtons. So the conversion, of course, is 19 times the 10 grams, 190 grams, kilograms, 0.19. Kilograms times 9.8 gets us to roughly 1.9 newtons. Okay, so let's measure. I'm going to hit the start button, and here we go. 1, 2, 3, 4, 5, 6, of course I'm counting in German, 7, 8, 9, 10, getting close, 11, 12. I think that's close enough. So I'm going to leave it at 29.5 seconds here. So let's look at the analysis. All right. So here's, of course, my example from earlier. So now I'm going to have a couple of examples here. For the applet, the angle was 0 degrees. And the number of rotations were 12 rotations in 30 seconds. Let's see what I come up with. So 1.9 newtons over here compared to 1.8 newtons over here with an error of 6%. Again, this is not a perfect applet because we actually have to take dynamic measurements just like you had to do with what I showed you earlier. Okay, let's try another one. I'm gonna use, let's see, a small amount of mass, reset first. So relatively small. Yeah, it does give kind of random numbers there. So 41, maybe I'm going to make this a small radius. There we go. And then, I don't know, lots of washers or few. Again, there's so many variables for this experiment. And then, whoa, that goes fast. I think that's the one I want. All right, let's give it a try. So I got 35 washers here, which will give me 3.4 newtons. Again, look at the conversion there. Then I'm going to have this one here looks like 45 centimeters. And then the mass is obviously 41 grams. All right, are you ready for me to count in German really fast? Here we go. Ready, set, go, or in German, auf die Plätze, fertig, los. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 23, 24, 25, 26, 27, 28, 30, 31, 32, 33, 34, 35, 36, 37, 38, 64. Wow. Okay, actually, I'm not too sure if I lost count here at some point. All right, so the analysis, here we go. Again, I have an angle of 0 degrees. And then here the 3.4, again, there were 35 washers, but converting 350 grams to kilograms and multiplying by 9.8 just doesn't come out to 3.5 newtons, just a little short, 3.4 newtons. And then I got the other numbers here, and here I got 64 rotations, if I didn't lose count, and I compare 3.4 newtons to 3.3 newtons with an error of 3% only. So I did actually count quite accurately. Somebody could say, hey, there is a difference of 0.1 newtons between the two numbers, just like the other ones, also 0.1 newtons, but why is the error quite a bit different? Well, the reason is that these sets of numbers is almost twice as much as the other set of numbers. So anyway, that's it for this particular lab. So I ask you to take another 6 measurements where you can adjust a lot of things on this one here. I'm going to reset it, adjust the mass, adjust the length, adjust the number of washers, count the rotations for 30 seconds, and so on. All right.